Welcome! In this session, we will tackle LeetCode problem number 287, titled Find the Duplicate Number. This is an interesting problem with multiple solution approaches, and we'll explore the most efficient one step by step. Let's dive in. In this problem, you are given an array of integers called nums, containing n plus 1 elements. Each of these integers falls within the range 1, n, inclusive. Importantly, there is exactly one duplicate number in the array, though it may appear more than once. Your task is to identify and return this duplicate number. Now, there are some key constraints you must follow. First, the array cannot be modified, so you need to work with it as is. Second, your solution should use only constant extra space, meaning the memory usage outside the input array should stay fixed. Finally, the time complexity should be better than O, in superscript 2, which rules out brute force approaches. To summarize, you must find the duplicate efficiently, without altering the array or using additional memory beyond a fixed limit. Let's now look at some examples to better understand the problem. In the first example, the array nums is 1, 3, 4, 2, 2. Here, the number 2 appears twice, making it the duplicate. Thus, the expected output is 2. In the second example, the input array is 3, 1, 3, 4, 2. In this case, the number 3 is repeated, so the output is 3. These examples illustrate how the duplicate number can appear in different positions within the array, but your solution must always identify it correctly. Here's another example to reinforce the concept. Consider the array nums equals 1, 1. This is the smallest possible input size for the problem, containing just 2 elements. Here, the duplicate number is 1, which appears twice in the array. The output, therefore, is 1. Now let's review the constraints. The length of the array will be between 2 and 100,000, and each element will be a positive integer between 1 and n, where n is the size of the array minus 1. Most importantly, the input is guaranteed to contain exactly one duplicate, so there's no ambiguity in the solution. Finally, let's think about some edge cases you might encounter. First, with the smallest array size, such as nums equals 1, 1, your solution must still correctly identify the duplicate. Second, consider cases where the duplicate appears at the beginning or end of the array, like nums equals 2, 1, 3, 4, 2, or nums equals 3, 3, 2, 1, 4. Third, if the duplicate occurs multiple times, as in nums equals 2, 2, 2, 2, 3, it's important to remember there's still only one duplicate number to return. Finally, for large input sizes up to 10^5, your solution must remain efficient and operate within the constraints. Algorithms like Floyd's tortoise and hare method, which use constant space and linear time, are well suited to meet these requirements. Keep these edge cases in mind as you design your solution. To solve the problem of finding the duplicate number in an array, we first considered a few potential approaches. One of the simplest strategies is the brute force approach, which involves comparing every pair of elements in the array. The intuition here is straightforward. If there's only one duplicate, eventually, comparing all pairs will reveal it. This method uses 2 nested loops to perform the comparisons, resulting in a time complexity of O, n squared. While it doesn't require any extra space, with a space complexity of O, 1, the downside is its inefficiency. For larger arrays, especially when n can go up to 10 to the power of 5, this approach becomes impractical due to its slowness. So, while it works in theory, it's not a viable solution for cases with stringent performance constraints. Another approach we considered is sorting the array. The idea here is that if the array is sorted, the duplicate number will appear consecutively. To implement this, we sort the array and then iterate through it to identify the duplicate. This method improves on the brute force approach with a time complexity of O, n log n, thanks to the sorting step. Depending on whether the sorting is done in place or by creating a copy, the space complexity is either O, 1, or O, n. However, there are significant drawbacks. Sorting modifies the input array if done in place, which might not always be acceptable. If a copy is used, additional memory is required. While it's faster than brute force, the use of extra space or the modification of the input makes it less than ideal. Another method we explored is using a hash set or a Boolean array. The intuition here is to keep track of the numbers we've seen so far, and as soon as a number reappears, we know it's the duplicate. This approach involves iterating through the array and adding each number to the set. If we encounter a number that's already in the set, we return it. This method has a time complexity of O(n), which is efficient, but its space complexity is also O(n), because of the additional storage required for the hash set. While it's a faster alternative to sorting and brute force, the extra memory usage is a limitation. The most optimal approach we considered is Floyd's tortoise and hare algorithm, which is based on cycle detection. The key insight is to treat the array as if it represents a linked list, where each index points to the value at that index. Because there is a duplicate, the structure naturally forms a cycle. Floyd's algorithm helps us detect this cycle and determine its entry point, which corresponds to the duplicate number. The implementation involves two main steps. First, we use two pointers, one moving slowly and the other moving quickly, to detect if a cycle exists. Once the cycle is detected, the second step is to find the entry point of the cycle, which is the duplicate. This approach is highly efficient, with a time complexity of O(n) for both detection and locating the entry point. Additionally, it has a space complexity of O(1), as it requires no additional data structures. The advantages are clear. This method avoids modifying the input, is highly efficient, and works well even for large arrays. These characteristics make it the most optimal solution among all the strategies we've discussed. Given the various approaches, we ultimately chose Floyd's tortoise and hare algorithm as the best solution for this problem. The reason is its exceptional balance of efficiency and minimal resource usage. With a time complexity of O(n) and a space complexity of O(1), it outperforms the other methods. The key observation that led to this choice was recognizing that the problem could be modeled as a cycle detection problem in a linked list. By treating the array indices as pointers, the structure becomes a directed graph with a cycle, where the duplicate number is the entry point of the cycle. This insight was the breakthrough that made this approach possible. In comparison, the brute force approach is far too slow for large inputs, and sorting, while faster, either modifies the input or uses additional space. The hash set method, though efficient in terms of time, uses extra memory proportional to the input size. Floyd's algorithm avoids all these drawbacks, leveraging the problem's inherent structure to provide an elegant and optimal solution. This makes it the clear choice for solving the find the duplicate number problem effectively. The problem we are solving is to find the duplicate number in an array nums of length n+1, where the numbers range from 1 to n. Importantly, there is exactly one duplicate, and it may appear multiple times in the array. The challenge is to achieve this without modifying the input array and while using only O(1) extra space. To solve this, we use Floyd's tortoise and hare algorithm, which is traditionally used for cycle detection in linked lists. We start by initializing two pointers, slow and fast, both pointing to the first element of the array. The slow pointer will move one step at a time by following the value at its current position, while the fast pointer will move 2 steps at a time. By treating the array as a graph where each index points to another index, the duplicate value creates a cycle, and the goal is to detect and locate this cycle efficiently. Once a cycle is detected, the next step is to find its entry point, which corresponds to the duplicate number. We do this by resetting one pointer, such as slow, to the start of the array, while leaving the other pointer, fast, at the position where the two pointers met during cycle detection. Both pointers are now moved one step at a time. The index where they meet again is the entry point of the cycle, which is also the duplicate number. Finally, we return the value at this index as the result. The key insight here is that the array can be visualized as a directed graph where duplicate values create a cycle, and Floyd's algorithm efficiently detects this cycle in O(n) time. Additionally, by reusing the array for traversal, we achieve O(1) space complexity, avoiding the need for any extra data structures. The algorithm relies on simple data structures, two pointers, slow and fast, and the input array itself, which is treated as a graph. The time complexity of the solution is O(n), because each element in the array is visited at most twice during the traversal. The space complexity is O(1), since no additional memory is used beyond the pointers. To illustrate, consider the example nums equals 3, 1, 3, 4, 2. Initially, both slow and fast pointers are set to the first element, nums 0 equals 3. This marks the starting point of the traversal. During cycle detection, the slow pointer moves one step at a time, while the fast pointer moves two steps. In the first iteration, slow moves to nums 3 equals 4, and fast moves to nums 3 equals nums 4 equals 2. In the second iteration, slow moves to nums 4 equals 2, and fast moves to nums 2 equals nums 3 equals 4. In the third iteration, slow moves to nums 2 equals 3, and fast moves to nums 4 equals nums 2 equals 3. Both pointers now meet at 3, confirming the presence of a cycle. To find the duplicate, slow is reset to the start of the array, nums 0 equals 3, while fast remains at the meeting point. Moving both pointers one step at a time, they meet again at nums 3 equals 3, which is the duplicate number. The output of the algorithm for the given example is 3. This approach is effective even for edge cases. For instance, in the smallest valid input, nums equals 1, 1, the algorithm correctly identifies 1 as the duplicate. Similarly, for an array where all values are the same, such as nums equals 2, 2, 2, 2, it still efficiently detects the duplicate. Even with large inputs, such as arrays of size up to 10 to the power of 5, the algorithm performs well due to its O(n) time complexity and O(1) space usage. Key optimizations include avoiding modifications to the input array by treating it as a graph and using the two-pointer technique to minimize memory usage. Overall, this algorithm is both time and space optimal, making it an excellent solution for the problem. This implementation solves the problem using Floyd's tortoise and hare cycle detection algorithm, an efficient approach with O(n) time complexity and O(1) space complexity. Here's a detailed breakdown. Step 1 *, we initialize two pointers, slow and fast, both starting at the first element of the array, nums 0. These pointers will help us detect the cycle caused by the duplicate number. Step 2 * using a while loop, we move the slow pointer one step at a time, nums slow, and the fast pointer two steps at a time, nums fast. This process continues until the two pointers meet, indicating the presence of a cycle. Since the array contains exactly one duplicate number, the cycle is guaranteed to exist. Step 3 * once the cycle is detected, we reset the slow pointer to the start of the array, nums 0, while keeping the fast pointer at the meeting point. We then move both pointers one step at a time, nums slow and nums fast, until they meet again. The meeting point is the entrance of the cycle, which corresponds to the duplicate number. Finally, we return the value of slow or fast, as both are equal at this point, as the duplicate number. This solution does not modify the input array and uses constant space, meeting the problem's constraints. It leverages the properties of the array in Floyd's algorithm to efficiently locate the duplicate number without additional data structures. Here, we are implementing a solution to find the duplicate number in an array using Floyd's tortoise and hare algorithm. The method starts by initializing two pointers, slow and fast, both set to the first element of the array. These pointers will help us detect a cycle in the array. The algorithm then enters a loop where the slow pointer moves one step at a time, while the fast pointer moves two steps. The loop continues until the slow and fast pointers meet, indicating that a cycle has been detected. Once we know there's a cycle, we proceed to find the entrance of this cycle, which corresponds to the duplicate number. To do this, we reset the slow pointer to the start of the array and continue moving both slow and fast pointers one step at a time until they meet again. When they do, the value at their meeting point is the duplicate number. Finally, we return this value as the result. The main method demonstrates how to call this function with a sample input array, and it prints the duplicate number to the console. The closing brace here simply marks the end of the class and method definitions. With this implementation, we've completed a robust solution for finding the duplicate number using constant space and efficient time complexity. By leveraging the Floyd's tortoise and hare algorithm, we ensure that this solution works effectively for arrays with a single duplicate, adhering to the constraints of the problem. This approach avoids the need for extra memory, such as hash maps or sets, making it both elegant and efficient. To solve this problem, we use Floyd's tortoise and hare algorithm. Let's start with the input array 1, 3, 4, 2, 2. First, we initialize two pointers, slow and fast, both starting at the first element of the array. Initially, slow is set to nums 0, which is 1, and fast is also set to nums 0, which is 1. Now, in step 2, we aim to detect a cycle in the sequence generated by these pointers. In the first iteration, slow moves one step forward to nums 1, which is 3, while fast moves 2 steps forward to nums 1, which is nums 3, resulting in 2. At this point, the state of slow is 3 and fast is 2. Next, in the second iteration, slow moves one step to nums 3, which is 2, and fast moves 2 steps to nums 2, which is nums 4, also resulting in 2. Now both slow and fast are at 2, indicating a cycle has been detected because the 2 pointers have met at the same value. Once a cycle is detected, we proceed to step 3 to find the entrance of the cycle, which corresponds to the duplicate number. We reset the slow pointer to the first element of the array, nums 0, which is 1, while fast remains at its current position, 2. In the first iteration, slow moves one step to nums 1, which is 3, and fast moves one step to nums 2, which is 4. At this point, slow is 3 and fast is 4. In the second iteration, slow moves one step to nums 3, which is 2, and fast also moves one step to nums 4, which is 2. Now both slow and fast meet at 2, confirming that 2 is the duplicate number in the array. This value is output as the result. Now, let's analyze another example with the input 3, 1, 3, 4, 2. Again, we start by initializing the slow and fast pointers at the first element of the array, nums 0, which is 3. In step 2, we detect the cycle. In the first iteration, slow moves one step to nums 3, which is 4, while fast moves 2 steps to nums 3, which is nums 4, resulting in 2. At this stage, slow is 4 and fast is 2. In the second iteration, slow moves one step to nums 4, which is 2, and fast moves 2 steps to nums 2, which is nums 3, resulting in 4. Now slow is 2 and fast is 4. In the third iteration, slow moves one step to nums 2, which is 3, and fast moves 2 steps to nums 4, which is nums 2, resulting in 3. At this point, slow and fast are both 3, indicating a cycle has been detected. To find the entrance of the cycle in this example, we reset the slow pointer to the first element, nums 0, which is 3, while fast remains at its current position, also 3. In the first iteration, slow moves one step to nums 3, which is 4, and fast moves one step to nums 3, which is also 4. At this point, slow and fast are both 4. Since the 2 pointers meet again, we confirm that the duplicate number is 3. This is the output for this example. Now, let's consider a simpler case where all the elements in the array are the same. In the final example, the input array is 2, 2, 2, 2, 2. Both slow and fast pointers are initialized at the first element, nums 0, which is 2. In step 2, we detect the cycle. In the first iteration, slow moves one step to nums 2, which is 2, and fast moves 2 steps to nums 2, which is nums 2, also resulting in 2. At this point, both slow and fast are 2, confirming that a cycle exists. To find the cycle's entrance, we reset the slow pointer to the first element, nums 0, which is 2, while fast remains at its current position, also 2. In the first iteration, slow moves one step to nums 2, which is 2, and fast moves one step to nums 2, which is also 2. Since the 2 pointers meet, we determine that the duplicate number is 2. This value is output as the result. The time complexity of this algorithm is determined by Floyd's tortoise and hare cycle detection method, which is divided into 2 main phases, detecting the cycle and finding the entrance to the cycle. In the first phase, we use 2 pointers, a slow pointer that moves 1 step at a time and a fast pointer that moves 2 steps at a time. These 2 pointers will eventually meet if there's a cycle, and the number of steps they take is proportional to the number of elements in the array. This ensures that the first phase runs in O(n) time, where n is the number of elements in the input array. Once the cycle is detected, the second phase begins. Here, one pointer is reset to the start of the array while the other remains at the meeting point. Both pointers then move 1 step at a time until they meet again, which will occur at the entrance to the cycle, or the duplicate number. This phase also takes O(n) time, as the traversal is linear and proportional to the size of the array. Combining these 2 phases, the overall time complexity of the algorithm is O(n). n. The space complexity of this algorithm is remarkably efficient, as it uses only a constant amount of additional memory. The slow and fast pointers are the only extra variables used for traversal, and no additional data structures, such as hash sets or arrays, are needed to store intermediate results. The input array remains unmodified throughout the process, and no copies of the array are created. As a result, the overall space complexity is O(1), or constant space. Furthermore, regardless of the scenario, whether in the best, average, or worst case, the time complexity remains O(n), and the space complexity stays at O(1). This consistency highlights the robustness of the algorithm for arrays of any size, making it both time and space efficient. When comparing this optimal approach to other methods, the advantages become clear. A brute force solution, for instance, would involve iterating over all possible pairs of elements to check for duplicates. While this approach is straightforward, it requires O(n²) time due to its nested loops, though it does maintain an O(1) space complexity since no additional storage is used. Alternatively, the hash table approach can reduce the time complexity to O(n) by storing previously seen elements in a hash set for quick lookups. However, this comes at the cost of O(n) space, as the hash set requires additional memory proportional to the array size. Another strategy is the binary search approach, which operates on the range of numbers from 1 to n1 and counts how many elements are less than or equal to the midpoint during each iteration. This reduces the time complexity to O(n log n), but like our optimal method, it uses O(1) space. Among these options, Floyd's tortoise and hare algorithm stands out for achieving both O(n) time and O(1) space, making it the most efficient in terms of memory usage. The mathematical proof of the algorithm's time complexity confirms its efficiency. In the first phase, the fast pointer moves through the array at most n steps before it catches up with the slow pointer in the cycle. In the second phase, both pointers traverse the array linearly, requiring at most n additional steps to locate the entrance to the cycle. Adding these together gives O(n) plus O(n), which simplifies to O(n). For space complexity, the algorithm uses only two pointers, slow and fast, regardless of the size of the input array. No additional memory structures are employed, meaning the memory usage does not grow with the input size, yielding an O(1) space complexity. In summary, this algorithm is optimal for the problem, achieving O(n) time and O(1) space. Not only does it outperform brute force and hash table approaches in terms of memory efficiency, but it is also well suited for handling large input arrays, making it a highly practical solution. Let's talk about some common mistakes to avoid when solving the find the duplicate number problem. First, modifying the input array is a frequent pitfall. While it might seem tempting to mark visited indices directly in the array, the problem explicitly states that the input array must not be changed. Always ensure your solution respects this constraint. Next, incorrect binary search implementation is another challenge. This approach isn't about finding an exact target value, but rather about counting how many elements are less than or equal to the midpoint value and adjusting the bounds accordingly. Failing to grasp this distinction can lead to errors, like setting incorrect bounds or even causing infinite loops. Some also incorrectly assume that the duplicate number will always appear in a specific position, such as the middle of the array. However, the duplicate could be anywhere within the range, 1en, so your solution must account for all possibilities. Lastly, edge cases are often overlooked. For instance, arrays with only two elements, arrays where all elements are the same, or cases where duplicates are at the boundaries can cause trouble if not tested properly. Comprehensive testing is crucial to ensure your solution is robust. Another common mistake is misinterpreting the problem constraints. The problem guarantees exactly one duplicate, yet some solutions incorrectly handle cases with multiple duplicates, resulting in unnecessary complexity or errors. Now, from an interview perspective, this problem is frequently used to test your grasp of efficient algorithms. For instance, Floyd's tortoise and hare algorithm demonstrates cycle detection, while binary search on a conceptual range requires a solid understanding of bounds management. Be ready to discuss both methods, including their time and space complexities. It's also important to highlight the trade-offs between approaches. Floyd's algorithm is space efficient, using only O(1) space, but its implementation can be tricky. On the other hand, binary search on the range might feel more intuitive but involves O log n iterations, Lastly, always emphasize that the constraints are key. Since the array is immutable and a duplicate is guaranteed, approaches like hash sets or sorting might work in other contexts but aren't optimal here. This understanding is critical to standing out during interviews. The concepts in this problem are closely related to several others on LeetCode. For example, LeetCode 142, linked list cycle, directly applies Floyd's tortoise and hare algorithm. Similarly, LeetCode 41, first missing positive, involves indexing within the array to determine values, which shares conceptual overlap. LeetCode 268, missing number, focuses on discrepancies between expected and actual values, much like this problem. Lastly, LeetCode 442, find all duplicates in an array, is a variation where you're tasked with identifying all duplicates rather than just one. Now, when it comes to alternative approaches, brute force has a time complexity of n squared. While it's simple to implement, it's inefficient for larger arrays and generally not recommended unless you're focusing purely on correctness. Sorting, with its n log n complexity, is easy to code but modifies the input array, which violates the constraints of this problem. Using a hash set achieves n time but requires extra space, making it suboptimal if you're aiming for the most space-efficient solution. Binary search on the range is an efficient n log n approach that adheres to the problem's constraints. However, it can be less intuitive for beginners because it involves counting elements relative to the midpoint rather than searching for a specific value. On the other hand, Floyd's tortoise and hare algorithm is optimal in both time and space, running in n time and using one space. The trade-off here is that it requires a solid understanding of how cycle detection works and how it applies to this problem. Mastering these two approaches gives you the flexibility to adapt to different interview scenarios, where the emphasis might shift between efficiency, clarity, and adherence to constraints. Both methods are highly valuable tools to have in your algorithmic toolbox. Great job! We've successfully solved the problem and discussed key takeaways. Remember to practice regularly and explore alternative solutions to deepen your understanding. Thanks for watching, and see you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!